Hello, everyone. My name is Tyler Flagel, and I am here with Gregory Mifflin, and we are both graduate students at Auburn University's GAV Lab. We are here today to talk about Arduino and provide information that will be helpful for your project.
So the Arduino was created in 2003 by professors at an Italian university. Their idea was to develop a low-cost microcontroller to outcompete the existing options on the market in terms of price. They named their invention after their favorite bar, which in turn was named after Arduino of Ivrea, who happened to be the king of Italy about a millennium ago. So what exactly is an Arduino? It's a microcontroller built upon the Atmel family of microcontrollers, which provides all of the necessary interface elements in one package. It has 14 input-output pins, 6 analog pins, and it can even store 32 kilobytes of memory. As an example of what using a microcontroller chip is like, let's consider the microchip PIC16F84 in the top left. To program the PIC, you have to use the socket pictured in green. It operates similar to a processor socket if you've ever messed around with computer components. From there, you can write your script to the chip. You then need to build your circuit around the chip. This includes several capacitors and resistors, as well as quartz, which is used for timing in the script. It also requires its own power source similar to an op-amp. Now consider the Arduino. The board already contains all of these things. To program the board, all you have to do is plug it into a computer through a USB. This makes it easy to pick up an Arduino and quickly prototype a new project. In general, microcontroller chips are better when mass producing a device, but an Arduino is better for one-offs or for proving that something will work. In order to understand the advantages of the Arduino, we found it necessary to answer why it's become one of the most popular platforms for low-level robotics. To prove this point, Amazon's choice for robotics is an Arduino kit. The first reason that Arduino has risen to such popularity is the fact that it's open source. Arduino provides circuit diagrams and other supporting documentation on the inner workings of the controller, and allows other companies to sell boards that are compatible with the Arduino IDE. In fact, you can even make your own Arduino from scratch by purchasing the individual elements and then assembling them if you so choose. We even found an instructables on how to construct it, although we're not quite sure why anyone would want to. Due to the reasons mentioned in the previous slides, the price of a non-name brand Arduino is relatively low. If so inclined, you can purchase an original Arduino board made by the original company and still manufactured in Italy. However, it will be twice as expensive. Personally, we've never used anything but knockoffs and have never had any issues. One thing to notice about the Elegoo board is that it has the name Uno, which is the name of the board that it's replicating, and also says that it's Arduino IDE compatible. Another reason that the Arduino has become so popular is the free IDE, which stands for Integrated Development Environment, which is usable with any of its boards. It's based on the C language and includes many helpful libraries that make life easy. You can even have servos, LEDs, and buttons running with just a few lines of code. Even unofficial Arduino boards can use this coding environment. Another reason that Arduino is popular is the presence of easy-to-use shields. These are boards which nest on top of the Arduino, which means that the pins match up and provide additional functionality. The examples included above can all be purchased on Amazon for less than $15, meaning you could, for instance, buy the Elegoo board, the data logging shield, and a photoresistor or some other low-level sensor for only around $30 total. So now I'll let Tyler discuss the technical details of the Arduino.
When someone says Arduino, most commonly they are referring to the Arduino Uno. However, there are two more variants we would consider in the mainline Arduino family. There's the Arduino Mega, which features more input-output pins as well as more flash memory, and the Nano, which features comparable specs to the Arduino Uno with a smaller area. It also features a micro USB instead of the USB serial or the barrel jack featured in the other two variants. The Nano features male pin headers instead of female pin headers. These male pin headers sink below the Arduino Nano and make it ideal for setting in a breadboard or perhaps a perf board and soldering it in. There are also many boards compatible with the Arduino IDE. There's the Teensy 4.1, which features much more memory than the Arduino Nano, despite being a similar size. It also features more pins. It also has a micro SD card slot. There's also the Adafruit Flora, which is designed to be used with wearable technology. It features a round footprint and also has comparable specs to the Arduino Nano. Its soldering joints are designed to be fabric safe. It is also designed to be sewn on. For a full list of compatible boards, we've included a Wikipedia link, which includes a relatively thorough list of all the boards you could potentially use. For the purposes of this presentation, we've included an example Arduino project in the form of providing a means to open a greenhouse vent. We want a user interface which contains a control knob in the form of a potentiometer, as well as a UI which provides a rough estimate of the vent position. Ideally, we would want this to be mounted, say, somewhere like next to a light switch or something like that, and provide the means to control it, even maybe when it's not in sight. So we say remotely controlled, but we really mean kind of in the same room, but perhaps not right on top of it. Say, for instance, that the vent is too high to reach or something like that. That's what we want to be able to control. So in order to accomplish this, we designed a circuit which features the Arduino Mega. Now, we chose the Mega because it was something we had on hand. You could design the circuit around the Uno or perhaps the Nano. Those would both work as well. So the circuit consists of three main elements. We have the potentiometer. We chose the 1K potentiometer. It has 3 leads, 2 of which are for power, are connected directly to the Arduino output power pins. There's also the signal line, which we connected to the A2 analog pin. There's also the 3 indicator LEDs. That's going to be our UI that roughly corresponds to the vent position. We have a red LED, yellow LED, and green LED. Each of them is connected in series with a 220 ohm resistor, which is then connected to one of the digital output pins. One thing to note about the LEDs is because they're diodes, current can only flow through them in one direction. One leg of the LED is going to be longer than the other. The longer leg is the positive leg. So that one's the one that needs to be connected to the digital pin, and the other needs to go in the direction of ground. Additionally, we have the 7.2 35 kilogram centimeter digital servo, all metal gearing. It is, because it's 7.2 volts, that's a larger voltage requirement than the Arduino itself can supply. So this means that it needs an external DC power supply. We use a variable benchtop power supply, but you could potentially control it through something else. One thing to note about the DC power supply and the servo is that they need to share a ground with the Arduino. This is what completes the circuit for the signal line connecting the servo to the Arduino. So this is what it looks like in real life. We actually built the circuit. It's not nearly as pretty as the diagram, but it gets the job done. So you can see the potentiometer, the servo wires, and the LEDs are all there, as well as the benchtop power supply. So now we're going to take a look at the code that allows the circuit to function. So taking a step back and looking at a framework of an Arduino code, we have an area, a code block responsible for initializing the variables. So oftentimes what I've seen is people will initialize whatever pin they're going to connect the circuit element to. They will also initialize any variables their logic uses. So say something like a counter or something like that. This is also where we're going to want to initialize any kind of libraries you might be using that aren't just built in like some of the other ones. You also will probably need to instantiate any kind of your classes in this block. There's also the void setup block, which is responsible for setting up your Arduino. So this is where you would assign pins to specific circuit elements. Then there's the void loop, which is where you would put your main code. This is going to be where all of the basically all the logic and everything that allows your project to function would happen. So this should be the heart of your script, will be in the loop portion. So seen here on the right is our greenhouse example. It's relatively long, so it's on the next slide. We've broken it apart. So you can see here that we've initialized our LED pins. We've also initialized the potentiometer pin and gave the potentiometer a variable and initial value. We've included the servo library and instantiated an instance of the servo class. And then in our setup portion, we've assigned the pins to the output for the LEDs, and we've attached the servo to a pin. So one thing to note is we didn't create a variable for the servo pin, but we easily could have. Alternatively, we didn't have to create a variable for the LED pins. So we've included examples of two ways, but it's not really required to do it one way or the other. It's more of a preference and convenience thing. Now, finally, we look at the loop, which is run repeatedly and indefinitely as long as the Arduino has power. The first line of code is responsible for reading whatever the potentiometer's value is. Next, we take that value and run it through the map function. And what this does is it establishes a relationship between the min and max potentiometer value and the min and max servo position. So say, for instance, the potentiometer value was halfway between 0 and 1023, it would output 90 degrees for the servo. So all it does is establishes that. Next, we're going to tell our servo to go to whatever position the output is. And now we have a series of conditionals which are responsible for lighting up the correct LED. So if the potentiometer value is less than 60 degrees, we want the green LED to be high. If it's greater than 120, we want the red LED to be high. And any other time, we want the middle LED, the yellow one, to be high. So the way this works is high is the maximum value, low is the minimum value, which would be 0. We also included the delay down here at the bottom, and what that does is it gives the mechanical elements of the project time to respond. If you recall Dr. Rose's conversation about time constants, you really want to make sure that the mechanical elements have time to react to whatever the circuit is telling. So we built and we ran the code and put it on the Arduino, and this is the end result. So you can see that it works pretty well. It even responds to whatever the potentiometer says relatively quickly when oscillating. So it's perhaps responds quicker than it would even need to. So now for some closing thoughts. The Arduino is really good for lower level tasks, so something like taking in a sensor reading, doing some low level processing, and then reacting perhaps with an actuator, LEDs, or something like that. Now, you could also consider the Raspberry Pi. Oftentimes, people kind of, I don't want to say they use them interchangeably, but they're often in the same conversation. I would think of the Arduino more as like a scooter and the Raspberry Pi more like as like a truck. You can do a lot more with the truck, but they can both get you somewhere. So there's a good example in these useful links, the Raspberry Pi versus Arduino. And what the guy says in the video is that, let's say you want to build a mobile robot that can operate based off of a Bluetooth controller. Now, if all you want to do is that, you can use an Arduino for that. However, if you want to do something like have a mobile robot with a webcam that can live stream to Twitch, you would want to consider something closer to the Raspberry Pi. The Raspberry Pi has USB ports and can handle the processing of information associated with a webcam. So really, you're going to want to look at whatever your project is. There's a lot of overlap between what an Arduino can do and what a Raspberry Pi can do, but the Raspberry Pi can handle much more complex tasks. Another thing we should probably mention is ROS compatibility with Arduino. So there's a ROS package which allows you to use Arduino. If you guys are going to be here over the summer, both of us would highly recommend Dr. Chen's robotics class for ROS. It would allow you to create more complex robots and higher level complexity tasks that these robots would be capable of. So for the most top part, real robotics is done in ROS, as you can do a lot more with that. But anyway, ROS serial is a package that would allow you to run a more complex task on a computer, say a neural network or complex vision algorithms. And then the Arduino would allow you to do something with those. So say move a servo or more complex actuation. And another thing I don't think we've mentioned in this presentation is that once you've written your script to the Arduino, it doesn't require the computer anymore. It can stand alone as long as it has power. So you can either power it through the USB serial jack, or you can use it through the barrel jack, which would allow you to use something like a 9-volt battery, allowing it to operate away from a permanent power source. That's about it. We're going to upload this video to YouTube. So if you guys have any questions, we'll do our best to answer them down in the comment section. So that's about it, and we really appreciate it.